In your study of kinematics, you have learned how to deal with the displacement, velocity, and acceleration of a body in motion without considering the forces responsible for the motion. However, in kinetics, you are going to study the variables of a body in motion along with the forces that are responsible for the motion. Let us take the example of the start of a football match. The football would not move until a player kicks it. If you want to load a barrel onto a truck, will it go up just by itself because you want it to? No. You have to either lift it or roll it onto the truck. In each of these cases, the body was at rest until an external force was applied to move it. Similarly, when a barrel is being unloaded from a truck using an inclined plane, it tends to roll down fast unless its motion is restricted by some opposing force. In this case, the barrel has a tendency to move faster, but is being restricted by a force due to an external agency. In all these examples, the external agency applying the force was in contact with the object in motion. Hence, these forces are known as contact forces. When you drop a ball out of a window, it falls down. How did the ball go down when you did not apply any force on it? The agency applying the force is the earth, and the force is called gravitational force. This gravitational force is invisible and is a non-contact force. If you take a magnet near an iron nail placed on a table, the nail moves. Here again, there is an invisible force acting, which is magnetic force. Magnetic force is also a non-contact force. In all these examples, we saw that an external agency applies a force, either contact or non-contact, to accelerate a body, which is at rest, or to retard the motion of a body, which is in motion. Thus, we can say that a force applied by an external agency either accelerates or retards a body. Now consider a body moving with a constant velocity. Is there a need for an external agency to apply a force to maintain this motion? Yes. External force is required if the body is in our world, where frictional force acts on all the objects. However, in the absence of friction, like in space, no external force is required to maintain uniform motion in a straight line. To answer this question without any ambiguity, we first have to go into the history of kinetics and see what mistakes were committed before Newton's laws of motion were postulated. Aristotle put forward his view. An external force is required to keep a body in motion. This seems to be right when you apply it to all the day-to-day activities taking place around us. For example, to pull a toy, a boy applies a pulling force on the string attached to the toy. As soon as he drops the string, the toy stops. It seems as if what Aristotle said holds well in this example. However, If you carefully analyze the external forces acting on the toy, you will find that the pull exerted by the boy is actually equal to and opposite to the frictional force between the toy and the ground, which is again an external force. And hence, the net force acting on the toy is 0. We can thus conclude that the force applied by the boy is not in any way responsible for the motion of the toy car. In fact, the applied force just helps in overcoming the friction experienced by the toy. This is an example from our existing world. Now, let us go into a virtual world where there is no friction of any kind. Then the boy need not apply any force to keep the toy moving with uniform velocity. This is exactly what Galileo said. Galileo proved that no external force is required to move a body with uniform velocity in the absence of friction. Galileo conducted 2 simple experiments before postulating the law of inertia. The first experiment was with one inclined plane. A roller rolling down an inclined plane on its own accelerates. A roller rolling up an inclined plane on its own retards. A roller rolling on a horizontal plane neither accelerates nor retards, which means that the roller should move with constant velocity when there is no friction between the roller and the horizontal plane. The second experiment was with 2 inclined planes. When the slope of the 2 inclined planes is the same, a roller released from rest on one plane rolls down that plane and climbs up the other plane to the same height from which it was released, or a little less. When the slope of the second plane is reduced, the roller climbs up to the same height, but this time it travels a longer distance. When the slope of the second plane is made 0, that is, it becomes horizontal, the roller moves infinite distance. This can happen only in a situation where there is no friction. Actually, the roller comes to rest after moving some distance as frictional force acts opposing the motion. From these experiments, Galileo concluded that in either case, the state of rest and the state of uniform linear motion with constant velocity, the net force exerted on a body by the external agencies is 0. Therefore, to maintain uniform velocity, the external force required is only equal to but opposite to the frictional force, such that the net external force is 0. Let us put the same statement in other words. When the net external force applied on a body is 0, a body that is at rest remains at rest, and a body that is moving with uniform velocity in a straight line will continue to do so. The tendency of a body at rest to remain at rest, or of a body moving with uniform velocity in a straight line to stay in motion with the same uniform velocity, when the net external force is 0, is called inertia. In simple terms, inertia means resistance to change or resistance to acceleration. Newton's laws of motion have their roots in Galileo's law of inertia. In fact, Newton's first law of motion is almost the same as Galileo's law of inertia. Newton's first law of motion states that every object continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. If you observe, there is no mention of acceleration in Newton's first law of motion. This is because when a body is in a state of rest, it has no acceleration. Similarly, a body in uniform motion in a straight line does not accelerate. Based on these facts, we can express Newton's first law of motion in two more very useful forms. 1. If the net external force on a body is 0, its acceleration is 0 and vice versa. 2. A body accelerates only when a net external force acts on it. These two forms of the law are extensively used while solving problems in kinetics. Let us apply what you have learnt in this module so far to analyze some day-to-day events. When you are standing on firm horizontal ground, what are the external forces acting on you? What is the net external force acting on you? Let us try to answer the first question. The first thing that comes to mind is your own weight, say 500 Newton. This force acts vertically downwards. Is there any other external force acting on you? You can now apply the knowledge from this module to analyze these situations. You are at rest. That means your acceleration is 0. Since you have already identified one external force acting on you, that is, your weight acting vertically downwards, there must be at least one more force which is equal but opposite to your weight, so that the net external force acting on you is 0. This force is the normal reaction between your feet and the surface of the ground. While attempting to answer the first question, you have also answered the second question. The answer to the second question is net external force acting on you is 0. Let's consider another situation. What are the external forces acting on you if you are standing in quicksand instead of on firm ground? Your weight is the same. But what about the normal reaction? It can't be equal to 500 Newton. It is definitely less than 500 Newton. How did you come to this conclusion? Simple. You are sinking into the quicksand. That means you have an acceleration vertically downwards, which implies that there is a net external force acting vertically downward. Let's take an example from a physics laboratory. An iron cube is placed on a glass sheet, which is fixed to a wooden plank. This wooden plank is hinged to a horizontal surface. The wooden plank is slowly tilted until the iron cube is about to slide down on its own. That is, without any external force being applied to it. This position of the inclined plane is known as position at impending motion. Theta is the angle between the inclined plane and the horizontal surface. We now have to identify the external forces acting on the iron cube. W Newton is the weight of the iron cube acting vertically downward. On resolving this force, W, along with x and y directions, we get Wx is equal to W sine theta and Wy is equal to W cos theta. As W and theta are known to us, Wx and Wy can be calculated. At the point of impending motion, the iron cube has the tendency to slide down, but is prevented by the frictional force, F, between the glass surface and the surface of the iron cube. How do you find the magnitude of this frictional force, F? There is no motion of the iron cube in the x direction. That is, the iron cube is at rest as far as the x direction is concerned. This implies the net force in the x direction is 0. Net force along x is equal to F minus W sin theta is equal to 0. Therefore, F is equal to W sin theta. The iron cube is not going into the glass sheet, which implies that the iron cube is at rest as far as the y direction is concerned. Hence, the net force in the y direction should also be 0. N is the normal reaction of the glass sheet on the iron cube. We can now write net force is equal to N minus W cos theta, which is equal to 0, or N is equal to W cos theta. We have used Newton's first law of motion to find the value of F and N, which were not known to us.
The momentum of a body is defined as the product of its mass m and velocity v. Momentum is denoted by P. Since mass m is a scalar and velocity v is a vector, their product, momentum p, is a vector. In the SI system, momentum is measured in kilogram meter per second or Newton second. Force, momentum and time are interrelated. Let us check some scenarios to illustrate this. A boy standing in a first-floor balcony drops a ball of mass m from a certain height h. As the ball goes down, it gains some velocity and hence acquires a certain momentum. A boy standing on the ground below catches the ball by using a force F. The momentum of the ball becomes 0 during the process of catching it, as it comes to rest. Another ball of mass 2m is dropped from the same height. This time, the force required to catch the ball is 2F. Between these two scenarios, the mass of the ball doubles, but the final velocity remains the same. Therefore, the momentum of the ball also doubles. Consequently, the force applied to catch the ball also doubles. Here, the momentum of the ball increases due to an increase in its mass. In the same scenario, if a ball of mass m is dropped from the second floor balcony from a height 2h, its velocity increases and therefore its momentum also increases. Consequently, more force is required to catch the ball. Here, the momentum increases due to an increase in velocity. In all these three scenarios, the ball has some momentum when it touches the hands of the boy catching it. However, the momentum becomes 0 as the ball comes to rest due to the force applied by the hands for some time. the force required to stop the ball and the length of time the force is applied are related to each other. A wicket keeper, after gathering the ball away from his body, pulls his hands towards himself to avoid injury to his hands. This proves that less force is required when it takes more time for the ball to come to rest. Now, let us look at another example, where the body is at rest initially. That is, it has zero momentum, and by the application of a force for a certain time, it acquires some momentum. A small car is at rest. 4 persons push the car for a certain length of time, at the end of which the car moves with a certain velocity. We say that the car has acquired momentum. A truck is at rest. The same 4 persons push the truck for the same length of time, at the end of which the truck moves with a velocity lesser than that of the car. However, the momentum acquired by the truck is the same as that acquired by the car. In these two activities, the force applied and the length of time for which the force is applied are the same. Therefore, the momentum acquired is also the same even though the mass of the car and the truck is different. Hence, a body of lesser mass moves with greater velocity compared to a body of greater mass, but the product of the mass and its velocity remains the same in both cases. In these examples, there was a change in momentum due to a change in magnitude of the velocity of the body. There was no change in the direction of motion of the body. What happens when the magnitude of the velocity of the body remains the same and only its direction of motion changes? Since the velocity vector changes direction continuously, the momentum vector also changes direction continuously, and this change requires some force. Consider a sling being whirled such that the stone and the thread rotate in a horizontal plane with uniform angular velocity. The magnitude of the linear velocity of the stone remains constant, but its direction changes continuously. To sustain this kind of motion, we have to continuously apply a pulling force on the thread. From these examples, we have understood that a force has to be applied on a body for some length of time, during which a change in momentum is taking place. In other words, the momentum of an object increases when it accelerates and vice versa. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion brings out this relationship between momentum, acceleration, and force. Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Consider a force F being applied on a body of mass m for a time interval of delta t seconds. This results in change of velocity of the body from initial velocity v to final velocity v plus delta v. Here, initial momentum p is the product of mass m and initial velocity v and final momentum p plus delta p is equal to the product of m final velocity v plus delta v. On simplification, we get the change in momentum of the body, delta p, as the product of mass m and the change in velocity, delta v. According to Newton's second law of motion, force is proportional to the rate of change of momentum. Bringing in the constant of proportionality k, the equation becomes F equals k multiplied by delta p by delta t. When delta t tends to 0, delta p by delta t equals dp divided by dt. This makes the above equation F is equal to k multiplied by dp divided by dt. Substituting p equals mv in dp by dt, we get dp by dt is equal to mdv by dt, or ma, since acceleration a is the rate of change of velocity v. Therefore, F is equal to kma, defines Newton's second law of motion. By choosing the values of k as 1, we can define the unit of force in the SI system. In the SI system, the unit force is one that causes an acceleration of 1 meter per second square to a mass of 1 kilogram. This unit force is known as a Newton. There are certain special applications of Newton's second law of motion. When no force is applied on a body, there is no acceleration in its motion, since the mass of the body cannot be equal to 0. This is one way to write Newton's second law of motion. Since force applied and momentum are vectors, we can apply the law by taking their components in the 3 coordinate directions, that is, x, y and z. Fx is equal to dpx by dt, which is equal to max. Fy is equal to dpy by dt, which is equal to may. Fz is equal to dpz by dt, which is equal to maz. F here stands for external force acting on the body. When a number of forces are acting on a body, we should take the net force in the equation as sigma F is equal to ma. Newton's second law applies to instantaneous force and instantaneous acceleration. Newton's second law of motion can also be written as change in momentum is equal to the product of force applied and the length of time for which it is applied. If a very large force is applied for a very short duration of time, it results in a large change in momentum of the body. This large amount of force acting on an object for a very short duration of time is called as an impulsive force or impulse. Measuring this force and time is difficult. However, the change in momentum can be measured, which is equal to the product of force and time. A bowler in a cricket match bowls a full toss ball and the batsman hits a 6. In this example, the batsman has applied an impulsive force on the ball, due to which there is a tremendous change in the momentum of the ball.
When a man applies a force on a wall, the wall offers an equal and opposite force, and the outcome of this interaction is that both the man and the wall are at rest. If the force applied is huge, deformation can happen in the wall and it may fall down. In this example, there are two bodies and two forces in this interaction. The question is, can we have only one force in an interaction? Let us try to imagine such a situation. A boxer tries to land a heavy punch on his opponent. The opponent intelligently sidesteps from the line of action of the punch. The punch goes waste. The boxer could not apply the force in the absence of a resistive force opposing it. From these two examples, we can conclude that forces always occur in pairs and always act on two different bodies. Newton put forth these facts in the form of third law of motion. Newton's third law of motion states that to every action there is always an equal and opposite reaction. Newton's use of day-to-day language in defining this law gave rise to some misconceptions. The two terms, action and reaction, seem like two different things. Actually, both represent the same entity, that is, force. The law gives an impression that action comes first and then its reaction. That is, action is the cause and reaction is its effect. Actually, action and reaction come into existence at the same instant. Action and reaction occur on the same body. Actually, action and reaction forces act on different bodies. Mathematically, Newton's third law of motion can be written as shown. Here, F12 is the force applied by body 1 on body 2, and F21 is the force applied by body 2 on body 1. The minus sign indicates the opposite direction. To avoid all these misconceptions, the Newton's third law of motion can be stated in a simple and clear way. Forces always occur in pairs. Force on a body A by body B is equal and opposite to the force on body B by body A. If two bodies A and B exist within a system, then force of A on B and force of B on A become internal forces of the system, and they cancel each other. Let us observe the recoil of a gun when a bullet is fired. The gun and the bullet are in one system. Initially, the gun and the bullet are at rest, which means the momentum of the system is zero. As soon as the bullet is fired, it moves forward with a very high velocity. Thus, there is a force exerted by the gun on the bullet in the forward direction. According to Newton's third law of motion, the bullet too exerts an equal amount of force on the gun in the reverse direction, which is referred to as the recoil of the gun. If Fbg is the force exerted on the bullet by the gun, and Fgb is the force exerted on the gun by the bullet, then Fbg is equal to minus Fgb. If delta t is the short amount of time for which Fbg acts, it is the same time during which Fgb acts. From Newton's second law of motion, the product of Fbg and delta t is the change in momentum delta Pb of the bullet. Similarly, the product minus FGB delta T is equal to the change in momentum delta PG of the gun. Initially, the gun and the bullet are at rest. Hence, their initial momenta PIG and PIB are 0. This indicates that the total momentum of the gun and the bullet as a system is 0. As the initial momentum of the gun and the bullet is 0, the change in momentum of the bullet and the gun is equal to their final momentum PFG and PFB respectively. Thus, the forward momentum of the bullet is numerically equal to the backward momentum of the gun, which is taken as negative. As the two momenta are numerically equal but opposite in sign, their algebraic sum is equal to 0. That is, the total momentum of the system is 0. We started with 0 momentum of the system, and its final momentum is also 0. This shows that the total momentum of the system is conserved. That is, it remains unchanged. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. System here refers to a conglomeration of particles or bodies. For an isolated system, there are no external forces acting on it. Let us apply this law to the direct collision between two bodies. Let the initial momentum of A before collision be PA, and the initial momentum of B before collision be PB. When A and B collide, there are two forces created, one on each body, for the same interval of time delta t. FAB is the force on A by B, and FBA is the force on B by A. These two forces are equal in magnitude but opposite in direction. Now, the final momentum of A after collision is P-A, and the final momentum of B after collision is P-B. Applying Newton's second law of motion to the two bodies, we get FAB delta T is equal to P-A minus PA, and FBA delta T is equal to P-B minus PB. Applying Newton's third law of motion, we get FBA is equal to minus FAB. Substituting the values from equations 1 and 2 in equation 3 and resolving, we get PA plus PB is equal to P-A plus P-B. This shows that the total momentum before the collision is equal to the total momentum after the collision. This proves that the law of conservation of momentum holds true for all isolated systems. Now let us look at the equilibrium of a particle. When the net external force acting on a particle is 0, the particle is said to be in equilibrium. Applying the Newton's first law of motion to this situation, we can say that the particle is either at rest or in uniform motion. When the particle is at rest, we say that the particle is in static equilibrium. And when the body has uniform motion, we say that the particle is in dynamic equilibrium. Let us check out the equilibrium of a particle with multiple forces acting on it. When two forces act on a particle and keep it in equilibrium, then both forces must be equal in magnitude but opposite in direction. and the two forces must be collinear. That is, the line of action of the two forces must be same. Now let's consider a particle in equilibrium with three forces acting on it. Here, the three forces must be coplanar, that is, they should all lie in one plane. The resultant of any two forces is equal to, but opposite to, the third force. The third force, which is opposite in direction to the resultant and whose magnitude is equal to that of the resultant, is called the equilibrant force. The vector sum of the three forces must be equal to 0. When n number of forces act on a particle and keep it in equilibrium, the vector sum of the n forces must be equal to 0. The vector sum can also be determined making use of the three components of the forces. Sigma F is equal to 0. Sigma Fx is equal to 0. Sigma Fy is equal to 0. Sigma Fz is equal to 0. Common forces in mechanics are gravitational force, which is the weight of a body, contact forces between moving pairs of links in a machine, tension in cables, and tension or compression due to elongation or compression in springs. In this module, we will focus on contact forces. An example of a contact force is the force between a box and the table on which it is placed. The contact force between the box and the surface of the table can be resolved into two components. One along the normal to the surface in contact, and the other parallel to the surface. The component perpendicular to the surface is called normal reaction, and the force parallel to the surface is called friction. Let us conduct a simple experiment to formulate an empirical relationship between normal reaction and frictional force. Place a cuboidal-shaped wooden block weighing 100 Newton on the wooden table top. The weight of the block will be acting vertically downward and will press the table top down. The table top will press the block up with a force equal to the weight of the block. The upward force of the tabletop on the wooden block is known as normal reaction. Let us now try to slide the wooden block by pulling the spring balance attached to the block. As we slowly pull harder on the spring balance, the friction force automatically increases and becomes equal to the applied pulling force. This automatic increase of the frictional force takes place up to a limit only. The frictional force at this point is known as limiting frictional force. At this point, the applied pulling force is equal to the limiting static frictional force. The block is at the point of impending motion. That is, the block is on the verge of moving but is not actually moving. We can repeat the experiment by placing the wooden block in different positions, such that different surfaces are in contact with the tabletop. We will find that the limiting frictional force is same in all cases. If we repeat the experiment by using a stone and an iron block in place of a wooden block, we will find that the limiting frictional force is different in all cases. Limiting friction increases as the mass of the block increases. We find that the limiting frictional force is independent of the contact area between the two surfaces. when the block actually starts moving. The frictional force experienced by the block is known as the kinetic friction force. The kinetic frictional force is always slightly less than the static limiting frictional force. From the results of this experiment, we can arrive at an empirical relationship between normal reaction and limiting frictional force. These empirical relationships are also known as the laws of friction. They are: static limiting friction is independent of area of contact. Static friction is proportional to normal reaction. It is equal to the product of mu s and n, where mu s is the coefficient of static friction. Kinetic friction is proportional to normal reaction. It is equal to the product of mu k and n, where mu k is the coefficient of kinetic friction. If the force F applied on the block is greater than the friction Fk, then the net force on the block is F minus Fk, and the acceleration A of the block is the ratio of the net force on the block to its mass. If F is equal to Fk, then the net force is 0, and hence the block moves with uniform velocity. If F is less than Fk, then the net force is negative, and it leads to retardation of the block. If we slowly increase the inclination of the surface on which the block is placed, there comes a point where the block starts sliding. At this point, the weight of the block, which is equal to mg, acts vertically downwards. If theta is the inclination of the surface with the horizontal, then mg sin theta acts down the plane and the static friction acts up the plane as shown. Thus, mg sin theta is equal to Fs. The normal reaction on the block acts perpendicular to the surface as shown, and it is equal to mg cos theta. As per the laws of friction, if mu s is the coefficient of static friction, then Fs is the product of mu s and n, which is equal to mu s mg cos theta. As the value of theta increases from minimum, the value of mg sin theta and as well as the value of Fs2 increases till the value of theta is equal to a maximum theta max. At this maximum value of theta, the block tends to move down the plane and experiences impending motion. Then the friction is limiting friction. In this case, mg sin theta max is equal to Fs max, implies mg sin theta max is equal to mu s mg cos theta max, which gives tan theta max equal to mu s on simplification. Now let us look at a rolling friction. When cylindrical or spherical shaped bodies roll without slipping on a cylindrical or flat surface, the frictional force is minimal. A ball or roller bearing fall in this category. To reduce the friction further, grease or lubricating oil is introduced between the surfaces. air is used as a lubricant in high-precision and high-speed equipment. Friction is desirable or undesirable depending on the situation in which it occurs. Friction between the moving parts of a machine is undesirable. We try to reduce friction by using lubrication. Friction is desirable when it occurs between the tires and the road's surface. Because of this friction, the automobile is able to move forward or stop when brakes are applied. We are able to walk only because of the friction between our feet and the ground. We would fall if we try to walk on a slippery surface. Have you ever wondered why a velodrome track is curved? Or, on a rainy day, while driving a car at high speed, what happens if you take a sharp turn on a flat road? You will get the answers to these questions in this module. You have earlier studied the acceleration of a body moving in a circle at uniform speed. Here, Fc, the force directed towards the center of the circular path, is the centripetal force. Centripetal force, Fc, is equal to mv square by r. A simple example of centripetal force is that of a stone tied to a string and rotated in a circle in a horizontal plane. The tension, T, in the string provides the required centripetal force. This tension in the string is due to the pull exerted on the string by the person, which prevents the stone from flying away. Similarly, a car moving along a circular path at uniform speed also requires a centripetal force to keep it moving along the desired circular path. In this module, we will analyze the forces acting on the car during this motion. Let us consider a car moving on a level, curved road. There are three forces acting on the car, namely, weight of the car, mg, normal reaction, N, and frictional force, F. As there is no motion in the vertical direction, the net force in the vertical direction is 0. We can say that normal reaction is equal to the weight of the car, mg. Let us call this equation 1. The static frictional force between the tires and the surface of the road opposes the impending motion of the car in the lateral direction away from the center of the circle. This frictional force, F, is less than or equal to the product of the coefficient of the static friction, mu s, and normal reaction, N. Let us call this equation 2. Substituting equation 1 in equation 2, we get F less than or equal to mu smg. Let us call this equation 3. The centrifugal force, Fc, is equal to the frictional force F. Let this be equation 4. However, Fc is equal to mv square by r. Where m is the mass of the car, v is the velocity of the car, and r is the radius of curvature. Let us call this equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get maximum velocity, Vmax, as the whole root of mu srg. That was about a car moving on a level, curved road. Now let us look at a car moving on a banked road. Let us analyze the forces acting on the car one by one. The weight of the car, mg, acts vertically downward. The normal reaction, N, acts upward perpendicular to the road's surface. The impending motion of the car in the lateral direction is away from the center of curvature in the lateral direction. The frictional force, F, acts opposite to this direction, that is, down the lateral slope. We can resolve the normal reaction, N, into its horizontal component, N sin theta, and vertical component, N cos theta. Similarly, the frictional force, F, can be resolved into its horizontal component, F cos theta, and vertical component, F sin theta. We can represent all the components of all the forces at a point C. Along with the weight mg as shown. As there is no motion of the car in the vertical direction, the net force acting along y direction is equal to 0. Or N cos theta minus mg minus F sin theta is equal to 0. This implies N cos theta is equal to mg plus F sin theta. Let us call this equation 1. We know that frictional force F is the product of mu s and n. Let this be equation 2. Substituting equation 2 in equation 1, we get equation 3 as N cos theta equals mg plus mu s n sin theta. The car experiences acceleration acting towards the center of curvature. This is the centripetal acceleration, and the force required for this acceleration is the centripetal force Fc. Centripetal force Fc is equal to the net force acting along x direction. This gives us equation 4 as N sin theta plus F cos theta equals Fc. Substituting equation 2 in equation 4 and solving, we get equation 5 as N sin theta plus mu s n cos theta equals Fc. But Fc is equal to mv squared divided by r. Substituting this in equation 5, we get equation 6 as shown. From equation 3, n is equal to mg divided by cos theta minus mu s sin theta. Let us call this equation 7. Substituting equation 7 in equation 6 and solving, we get the maximum velocity, Vmax, as shown. Now, dividing all the terms on the right-hand side with cos theta, we get equation 8 as shown. If the frictional force is negligible, the maximum velocity, Vmax, is equal to the whole root of rg tan theta. There is a systematic way to tackle problems in mechanics. Draw a free body diagram. Choose convenient coordinate system. Consider all the forces acting on the body. Resolve the forces in the chosen coordinate system. Apply Newton's laws of motion and solve all the equations to find the unknown variables. Let's take a look at each of the steps involved. To draw a free body diagram, we need to draw a schematic diagram showing all the bodies in an environment along with their links and supports. Then, we consider a convenient part of this diagram, relevant to the problem at hand, as a system. Then, we draw a detailed diagram of this system along with the external forces acting on it. This diagram is known as a free body diagram. This completes step 1 of the solution. In a free body diagram, we do not consider the forces applied by the system on the environment. Next, we choose a convenient coordinate system to resolve the forces involved. Coordinates should be chosen keeping in mind the probable direction of motion of the body. This makes the solution easier. Then, we add details about all the known and given forces on the system, indicating their respective magnitude and direction. Then we resolve all these forces along the chosen coordinate system. Finally, we can take the help of Newton's laws of motion to determine the magnitude and direction of unknown forces. If the problem at hand requires an analysis of multiple systems in an environment, we follow the same procedure for each individual system. To understand these steps, let us take a problem and solve it systematically. Bodies A and B of mass 10 kilograms and 30 kilograms respectively are connected by a rope of negligible mass passing over a frictionless pulley. The coefficient of friction between the masses and the inclined planes is 0.30. Determine acceleration of the system, tension in the rope, velocity of the system at the end of 4 seconds starting from rest. First, we draw the free body diagram. Here, as the two bodies are connected by a rope, we split the problem into 2 parts and tackle them independently. As the mass of B is greater than the mass of A, and the inclination of the plane on which B is resting is greater than the inclination of the plane on which A is resting, B is likely to go down and A is likely to go up the plane. Next, we choose a convenient coordinate system, XY, such that X is parallel to the inclined plane and Y is perpendicular to it. We choose X parallel to the plane, as body A is likely to move along the plane. This will make the application of Newton's laws of motion easier. Then, we denote the forces on body A, which are its weight, mg or 98.1 newtons, and tension in the rope T, which is unknown. Next, we resolve the weight of body A along x and y coordinates. The x component is equal to mg sine theta, which is equal to 49.05 newtons. Similarly, the y component is equal to mg cos theta, which is equal to 84.96 newtons. As there is no motion of A in the y direction, we can say the net force along y direction is 0. Summing up the forces acting along y direction and solving this net force equation, we get the normal reaction N as 84.96 newtons. Let us call this equation 1. As A is moving up the plane, the frictional force F acts downward. F is equal to the product of the coefficient of friction, mu, and normal reaction, N. Substituting the value of N from equation 1, we get the frictional force F as 25.49 newtons. Let this be equation 2. As A is moving up the plane, we take the inclined plane's upward direction as positive. Using Newton's second law of motion, the net force along x direction is the product of the mass of the body A and its acceleration. Substituting values and solving, we get equation 3 as t minus 74.54 is equal to 10 times the acceleration of body A. Now consider the other part, that is, body B, and draw a free body diagram indicating the forces and a convenient coordinate system. The weight of the body B acts vertically downwards. This force can be resolved into its x and y components as mg cos theta and mg sin theta. Mg cos theta is equal to 147.15 newtons and mg sin theta is equal to 254.87 newtons. As there is no motion of B in the y direction, we can say the net force along y direction is 0. Summing up the forces along y direction and solving, we get the normal reaction N as 147.15 Newton. Let's call this equation 4. As the body B is moving down the plane, the frictional force F acts upward. F is equal to the product of the coefficient of friction, mu, and normal reaction, N. Substituting the value of N from equation 4, we get the frictional force F as 44.15 newtons. As the body B is moving down the plane, we take the inclined plane's downward direction as positive. Applying Newton's second law of motion, the net force along x direction is the product of the mass of the body B and its acceleration. Substituting values and solving, we get equation 5 as 210.65 minus t is equal to 30 times the acceleration of B. Since A and B are connected to each other with a rope, the magnitude of their acceleration is equal. Substituting equation 6 in equations 3 and 5, we get t minus 74.54 equals 10a as equation 7 and 210.65 minus t equals 30a as equation 8. Equations 7 and 8 are simultaneous equations with two unknowns, which are t and a. Adding these equations and solving, we get acceleration as 3.4 meters per second squared. Substituting the value of A in equation 7 and simplifying, we get the tension in the rope T as 108.54 newtons. Now, we need to find the velocity at the end of 4 seconds. Given that the initial velocity of the system, v0, is equal to 0. Acceleration of the system, a, is 3.4 meters per second squared, and time t is 4 seconds. We can use the equation of motion. V is equal to v0 plus at to determine the velocity at the end of 4 seconds. Substituting the values and simplifying, we get the final velocity, v, as 13.6 meters per second. Another way to solve this problem is that we can combine the two bodies, A and B, along with the rope into a system. Tensions T, acting on body A and B, now become internal forces, and hence cancel out each other, and will not be taken into consideration while writing the net force equation. The net force of the system along x direction is equal to the product of the total mass of the system and its acceleration. Substituting the values and solving, we get the acceleration a as 3.4 meters per second squared. The disadvantage of this method is that the tension in the rope T cannot be found directly. To find T, we have to write the net force equation for A or B, where we substitute the value of acceleration just obtained, that is, 3.4 meters per second squared. Let's consider the net force on body A along x direction, which is equal to the product of the mass of body A and its acceleration. Substituting the values and solving, we get the tension in the rope T as 108.54 newtons.